I'm Nickoli. This is Riley Turchak.
Everybody?
And we have done the model rocket engine test stand project for our Capstone. So, to give you a quick rundown of what our presentation is going to look like, these are all our topics we're going to talk about. So we're going to look at what the project entails, the requirements, for review some past designs, go over our possible design concepts that we've crafted. We'll look at how our design meets the requirements. We'll look at what we've created and what we selected. We'll look at material component selection and prototyping. Talk briefly on calculations, show you some drawings, and look at the circuitry we've done. Go over the testing and the results, future design improvements that we could do. Give you a conclusion, and then we'll have a questions period. So I'll hand it to Riley, and he'll talk about what our project entails.
So what does our project entail? The purpose of this test stand you see here is to test the thrust output of these model rocket engines here. They come in various sizes, as you can see here, varying from quite small to quite large. They're a simple black powder device, and the purpose is to determine how accurate the thrust plots provided by the manufacturer are to the actual existing engines. The purpose is also to potentially design nozzles or custom model rocket engines for the future of the mechanical engineering department as a fun project, or looking at results. Plenty of things you can do with it. Here's the requirements that we came up with. Some of these requirements were stuff that we determined ourselves. The rest were stuff that was required, given from our supervisor. You can see here, we rated them with a comparison chart, not listed here, but that is where we got these numbers. You can see at the top is low manufacturing time. We did not have a lot of time for this project, as everyone's mentioned, 3 months. Pretty tricky to make something, so we listed that as our highest. Easy engine loading, stuff like that. The most important consideration and unique thing with these model rocket engines, you can see here they have a parachute, to launch this parachute, the engines actually have a parachute charge. And the problem with this is to measure the thrust, you need a sensor. You want to push down on the sensor with the engine, but unfortunately with this charge here, you'll be blasting your sensor directly. It's a sensitive device. That's not a good thing to do. So it was a tough thing to design around, and that was probably the most important hurdle that we had to get over with this design. Pass it back to Jared here for some past designs in a minute, but first of all, we'll discuss this design. So the main thing with this project was that in last year, it was actually 2 designs were made here by 2 previous students. The first one here I'll talk about is the linear rail design. This design was one of the 2 that was the most functional. They got some readings out of it, but it had some issues with the roller bearings it used, some tolerancing issues, as well as some folding issues. And then I'll pass it to Jared to talk about the inline design there.
Yeah, so the second design that came up with last year was the inline design, and it functioned similarly by acting on a chassis to push into the sensor, but this one used linear roller bearings. So it would sit in a carriage here and then push into the sensor. This one used a cartridge style of loading, that the engine would be placed into this 3D printed cartridge with the fasteners, and then would be fastened down. This was time extensive for loading and unloading, and was very custom to the one size of engine. Now there are multiple sizes of engines that have the same dimensions, like this D12 and this C11, so that's not such a big concern, but to have to completely undo this with its fasteners every single time to do a test firing, it takes too much time. Another consideration was this stand never was truly fired. The sensor that they wanted to use never arrived due to shipping errors. And the last consideration that kind of put this one to the side for us was the amount of 3D printed components. On the linear rail design, after a few test firings, there was some damage from the parachute charge on the 3D print, causing a bit of melting issues. So for this one to have the various 3D printed components, we wanted to avoid that in our design. So here we have a few of our designs that we came up with. Initially, we started with what we call the cannon design, and it uses a housing and bushing style of loading, like all of these designs do. This one we weren't such a fan of because the engines here in the bushing would press directly on the sensor without any kind of mediator, and we weren't a fan of that for multiple reasons. It was also quite robust, and we figured we could improve on it. Our next concept we developed was the rotary design. This separated the engine and exhausts from where the sensor is located, but was deemed complicated. There's a preload that we would want to have on the sensor, so having the device rest on the sensor initially, so there isn't an impact load from this arm. We were trying to come up with some concepts on how to preload it, which eventually led us to the hinge design. The hinge design has a constant preload and it uses gravity force, which we know and can use relatively well for calculations and verification. And it sort of developed from the rotary as well. We noticed that the rotary design hinges here in the center, and then we kind of took the hinge there and put it over here. So this hinge design that we came up with is a very low friction hinge. As we can see here, we didn't want any friction for any bit of loading for the engines pressing down into the sensor, because we figured that could interrupt with the data collection, and we wanted to avoid that. Quick note, the bushing and housing idea came from these caliber adapters for firearms. So these are 12 gauge cartridges, which is a rather large diameter, and this is a 22 cartridge. This adapter allows 12 gauge shotgun to fire a 22 rimfire cartridge. And this was a helper in our idea of concept creation. Now, Riley will tell us about our requirements.
So how do our designs meet these requirements that I've outlined? As we just discussed a bit on that last slide, we did end up going with the hinge design, but here's the breakout of how it ended up going. We have our criteria here. We used the rail design concept from last year as our datum. Given that it was the most complete, it worked the best. And then we compared our concepts against it. The Canon design didn't have any benefit over the old design, mostly because of the alignment of the sensor directly with the engine and the parachute charge issue, as I mentioned previously. The rotary was pretty good, close to the hinge design, but mostly lost out due to complexity, difficulty in machining, and also the troubles with the preload, as Jared mentioned. This uses gravity. Don't have to worry about it swinging around and banging your sensor. Delicate component, you don't want that to happen.
So to talk a little more on our selected design, we show here the 3D model that we created, which is very similar to what we actually were able to produce. And here's a section view of how it goes together. We have it here on the table as well, so they're both very helpful. The hinge design here incorporates these bushings, like I was talking about, and this is what holds the engine. So to load this, you would put nozzle end up to the top of this bushing, and then you insert, like so, into the housing, tightening the lower set screw first to ensure straightness in the bore, and then the top set screw here holds in this channel in the bushing to prevent the bushing from pulling out of the housing. Down here at the base as well, we have what we call our safety bolt. That prevents the arm from resting on the sensor. It prevents any shock loading when this is being transported or stored, or in between tests. You thread out the safety bolt to prevent contact of the sensor. Some of our material and component selection, we selected aluminum for the majority of the stand. It was readily available in the shop, and we were familiar with the characteristics of aluminum and machining with it. Aluminum doesn't degrade, well, I guess in theory it can, but it doesn't degrade any harsh characteristics like a 3D print plastic would in this aspect. Yeah, we got our fasteners from the shop. We have hardened fasteners here, and then we have our pin here. This holds the bushing in the housing. That's what it puts all the force on. And then we have another 11/64 pin here where the main hinge occurs. And some prototyping. This here is practically what you see on the table, but with a different hinge design. That hinge design was a lot more basic than what we have now. It just had these little holes where you would line up the pin, and they would rotate in there. The theory was to lubricate that with graphite so that it wouldn't have high resistance, or high friction, I guess, when in that. So I'll pass these around, we can look at. And then we eventually got to the hinge design we have now, which incorporates a bearing being held here, and then a threaded fastener to put tension and some clamping force down on the bearing to prevent the outer race from rotating. I'll also pass these around. Along with our prototyping, we did a cost estimation, and the consumable cost estimation for what we made here, the material we used, is around $230. With labor costs and overhead costs, manufacturing and all that, it gets up to be around $1,400 after all that kind of thing. To talk a bit on calculations, I evaluated the stand in a few different ways. The first calculations I did were to evaluate the arms characteristics. So I assumed a 15 Newton load would be applied from our engine into the device. And I found that the highest shear and the highest moment stress is here, where the arm comes in contact with the sensor. After doing the calculations, we had a safety factor of 2,600, which was deemed quite acceptable in our opinions. We did some other calculations as well. We looked at the double shear on the pin, and we looked at bearing stresses on the housing. The double shear in the pin acts in here on each location of the pin in the housing, right in there. So we did those calculations using a 15 Newton load and then as well a 150 Newton load. And with the 150 Newton load, our lowest safety factor was 81. And when looking into some standards for solid rocket engine testing, we found that NASA actually has a document on it, and their highest safety factor, or their recommended safety factor, is 4. So 81 is okay in our books. Here is the very first drawing of the assembly package. This shows a section view that you've already pretty much seen, and a nice symmetric view that we can see. And the next two drawings should show us the difference in the bushings. So this is the A8 and C6 size bushing. So it's got a thicker wall there to suit the different diameters. So these are two different engines, an A3 and a C6, and they both fit in here with a good diameter. They have a small bit of play, but that made no difference in the actual testing. And the length characteristics of these engines are the exact same. So holding is done quite well with the bushing style. The next one should be the C size, which holds the D12 and the C11 in the same fashion. The D12 is 25 thou longer and doesn't make the biggest difference in engine holding. So it's nice that they're similar lengths.
So now onto the circuit. There's two halves of this project, a physical thing, as you can see here, and then we had to actually analyze this data, and that fell to me. So here we have the load sensor. This is the same load cell that was used by last group's project. You can see it there. We have it applying the load basically right onto here between these two bolts. What this, as discussed in another group's project there, this is a Wheatstone bridge load cell. It measures a change in resistance with deflection of the sensor. However, this voltage that is outputted here is quite low. So what we needed was an amplifier, and then we needed a digital to analog converter to get that signal into something that can be read on a computer. So what we ended up going with is here we have a SparkFun load cell amplifier, and what it is it's basically just a simple little circuit that boosts that signal into a higher voltage range that makes it easier to read. We actually ended up using a lot of SparkFun's resources. They're an open source company. They basically are there to making projects like this easier for people. So not only did we use their sensor, but with this Arduino here, we actually also used their open source code. Had to modify it slightly to meet our demands. But what that code did is it takes a reading at a certain set time. Initially, we had it running at 10 samples per second. However, as we'll see here in a few seconds, with the graphs that we did the first test, it didn't give us the resolution we needed to actually be able to determine how accurate the sensor was, how close the engine was to the max force that it will actually have based on the manufacturer recommendations. So we then later ended up going with an 80 sample per second rate, and that got much better data. First thing we had to do though was with this software, it basically just takes the voltage and with a simple formula gives you a Newton equivalent or whatever unit you'd like. So to actually make sure it's giving you the readings you want, we had to do some calibration. So what we did was we took some samples of metal here, measured their mass on a scale down in the shop there, calculated the Newton equivalent that it should have, and then put it on our stand and got the calibration factor, played around with it until we actually got readings out of it that we should. And the end result was, as you can see here, quite close, an average of, I think it was 0.2 newtons, or 0.02, sorry? 0.2. So it was fairly close. Some of the, we tested a range of weights as well to make sure that a higher force wouldn't lose accuracy versus a lower force as you go through the different range of this load cell. And everything looked pretty good, so we then moved on to doing some testing. So this is the initial engine holding testing that we did. You can see here the arm, which is now in the thing. This was just to test our bushing design, make sure nothing would go flying, get loose, be dangerous. Everything worked great, so then we moved on to doing some full circuit testing and testing. So you can see here the setup that we used outside the building there. We had, of course, the laptop, the circuit, and the test stand, measuring the data. And then to actually ignite these rocket engines, you need a voltage source, so we used a power supply there, and then of course fire extinguisher for safety. We have here just a photo of the test so you can get an idea of what it kind of looks like. And then here I'll show you guys a video of a C11 test. This was one of the first tests we did with the 3D printed hinges, which are being passed around. And I'll play the video. One thing to note here, this isn't slow-mo, so this is not representative of the actual duration of the test. These motors only fire for approximately 2 to 5 seconds. It's quite a short burn time. And here we have the D12. This was one of the bigger engines we did. This video is at an even slower rate. Got a nice close-in shot here to try and determine how the load cell will be affected, how the wires are being managed. You can see here it starts off quite strong. The way these engines are designed, they have a peak force pretty much immediately, peters out to a lower level here, and that gets you up to the maximum height of your rocket, the apogee. And then once it gets to that height, after a delay, the parachute charge is deployed, and then the rocket comes back down, as you can see here in a second.
Yeah, so the D12 has a longer runtime than the C11. It has more charge packed into it, but is the same size, like I had mentioned. The C11 has less of a fuel burn, and that's why it's quicker.
The main thing to note there with that parachute charge going off is that it was a lot stronger than we expected. So in the future, type of shield should be implemented to keep the sensor from being damaged. Here's just some thrust graphs I'll go through quickly. These were the initial ones at the 10 samples per second that I mentioned. Not very good data, very peaky. Here's the smallest engine, the A8s that we were testing. A slightly larger engine, a little bit better data because of the longer runtime, still not quite what we wanted. Same thing with the C11 and D12. And then we moved on to doing the 80 samples per second. So here's a stack of the 3 tests that we did of each engine onto one graph, so we could compare the results. As you can see, it matches fairly close with the manufacturer's thrust plots. However, this thrust plot we don't really know the accuracy of it. It's just a representative thing. The main thing to note here is the differences between the different rocket engines could be differences in packing of the charge. Here you can see on the C11, same kind of thing, different durations, different peak thrusts, just variations in packing. Here's an interesting result we had with the C11, where one of the engines actually had a failure of sorts, where it didn't have the normal duration. It kind of instantly almost exploded on us. And you can see it measured a very high peak thrust and then died out. So you can kind of see some of the engines will be faulty. Interesting to compare the results there. And then the D12 there. And then here's a comparison of all the different rocket engines we tested, so you can see it, get an idea of the scale and the different thrust outputs as well as how long they burn for. Yeah, and then we'll move on to some future design improvements. So some of the things we noticed, well, having an Arduino and amplifier just kind of sitting on the ground kind of sucks. There's water around, not great. So we need to develop a mounting panel of some sorts to keep those components dry. Other thing with that circuit there, I just used some wires there that are easily pulled out. So in the future, a soldered connection would have to be made. Limited time, we just had to get something working. And then another thing we came up with was the alligator clips here. The management wasn't very good. So you have basically a live wire falling down towards a conductive base. You need to maybe have a clamp or something to hold the wire so that can't happen. And then the other thing is, instead of using a power supply, we could use a Estes launch controller, which has a safety lockout. Doesn't have, it's not a big power supply that you have to lug out into the cold. This is something that smaller and easy to carry around, and is designed for actually doing this kind of thing.
Yeah, so it's just a little 9-volt battery operated. Like you said, you wouldn't have to plug it into something or rely on an outlet being nearby. Some other bits of improvement we can make are some sensor shielding. This image fantastically demonstrates why sensor shielding is important. And that could be implemented relatively easily. There's a bit of a gap here between the arm and the housing body itself, and you could shim a bit of plate in there to separate the two areas from the firing incidents. And also more bushings can be turned. So we selected these two because these engine sizes were readily available at the hobby shop in town. But if the college wants to pack their own rocket engines, longer bushings can be used, different sizes of bushings. It is only limited by its inner bore on the housing. Yeah. So, in conclusion, well, you've made a functional prototype and it collects data. Rocket thrust capabilities have been measured. We've completed a series of tests and they seem to have done well. Further testing can be completed. We feel that this device, due to its low friction hinge and its strong engine holding, is rather precise. And we've put a lot of time into it, as everyone has on all the capstones this semester. So yeah, that's our project.
Any
Thanks
questions?
for listening.
Okay, questions to the presenters?
This looks really good. One thing with the image there, one of the things that I see right away is a moment arm. Did you take into account the fact that you're going to get a force multiplication issue?
So we did consider that initially. We did do some calculations to figure out a correction factor that might be implemented. But what we ended up doing was, on the calibration slide there, we had the weights applied right on here, so where the force is roughly going to be applied. And then that calibration factor, how we adjusted it to get the good readings, basically it takes that into account. So you're compensating for the moment arm in the calibration factor.
Yeah, it's like a built-in transfer function sort of thing.
Yeah. Good words.
I'm sure you guys have been there.
Actually, I've got one more question.
Sure.
So one of the other big differences I see right away is that in a normal rocket, the engine points down, whereas when it points upwards. Do you expect that to change the results at all?
We don't expect it to. Since these are solid rocket engines, the direction it burns in isn't necessarily important. If there's a liquid engine, of course, that would not work. But for these, given how simple they are, it shouldn't affect things too much. Sebastian?
Is there a limit to how long your rocket engine can be to test it? Like, at what point do you start thinking that this is too long?
The limit is your imagination.
Yeah.
So, for as long as you can build a rocket engine and you can turn a bushing to go around it, you're good to go. The mass of the bushing, again, like Riley was saying, it doesn't affect the results going on with its mass. So if you can turn a bushing to be, you could have a foot-long rocket engine. It'd be a huge rocket, don't know why you'd want it, but you could. So it's really, if you can turn it, you can make it.
The important thing with that would be, the limit would be the sensor itself. It has a 5 kilogram limit. So if you, that would be your upper limit.
Yeah.
Owen?
That's the question segues into my thoughts, like if you altered your mounting style to a collet style and shifted the retaining to the bottom of the rocket engine, any excess length would go up and
Yeah.
not. You wouldn't require this variety of bushings.
It already does go up.
Yeah, correct, but your holding system is what you're requiring different lengths of bushings.
Yeah, the length of the bushing, there's that, you know, you turned one for us. There was a step on the inside that holds the end of the engine, so that would prevent any bit of movement to come out of the top. That was our design to have a fully concealed engine to prevent any bit of shifting around in the bushing. But there could be other methods of holding that don't require that, but this is what we've produced.
Yeah, the parachute charge was the reason we put that in there, because as you can see in that video, it's pretty strong. Maybe not a lot of thrust, but if it was just an open thing, it would surely go flying. We did consider doing a collet design, as that would be great for different sizes, but the problem would just be the manufacturing of it. That was basic, otherwise it would be great.
Any other questions?